Okay. So we have a problem here. It's that a spherical balloon is being inflated by pumping in air at the rate of 400 centimeter cubed per second. So you know that centimeter cubed, let me put centimeter cubed, that's volume. But I said per second, that is 400 centimeter cubed per second. So we know that this is a volume, right? Isn't it? But it's a volume which is in terms of time. The volume changes in terms of time. Centimeter cubed per second. The T represents time. So it's being inflated. So inflated means what? Uh, inflated means what? Mm. It's vice versa. If you're relieving the, let's say, for an example, in a tire, you're relieving the air, isn't it? Yeah, or maybe English. Or inflated. Yeah. Inflated by pumping in air. So we had said pumping in air at a rate of 400 centimeter cubed per second. Hey, he looks confused. Yes, inflation, yeah. All right, yeah. So we're pumping in air at a rate of 400 centimeter cubed per second. So calculate the rate of increase in the radius when the radius is. So at number one, the increase of radius. When the radius is 10 what? Centimeter. So let's calculate the rate of increase in the radius when the radius is 10 centimeters. So let's look into a sphere, right? A spherical uh, balloon. So it was a balloon. Spherical balloon. So let's say we pumped in air there. Let me just do the radius thing. That's diameter. Let me cut it in half. We'll have radius there. So which means when you keep on pumping air, it means that it can increase maybe to that R size again. So which means this R keeps on increasing. We'll end up even having R2 then. So the radius is increasing. So at least we know that for a sphere, I think in the formula sheet, for a sphere, V is equals to 4 over 3 pi cubed, right? So it's 4 over 3 pi. I'm saying pi, but I'm not writing pi. So pi r cubed. So it's 4 over 3 pi r cubed. So we need to determine the rate of increase in the radius when the radius is 10 centimeter. So if we're given the following here, so it means that we need to determine number one, dr, the rate. So when you talk about the rate, your rate, it's time. We are rating it or maybe measuring the increase of radius in time. So it can be in seconds. So here it's seconds. So it means that per second, we need to rate the increase of the radius. So TR over TT. So which means, as we know initially, we're given the volume. So now we can manage to get our increase, the rate at which the radius is increasing. So we'll say dV over dt, change the volume in terms of time. So therefore it will be equals to, so 4 over 3 pi, it is constant, but we need to change the radius in terms of time. So derivate the radius in terms of time. So it is going to be 3 r squared multiplied by dr over dt. Change the radius in terms of time. We're not changing it in terms of r, but in terms of time. Change the radius in terms of time. So hence we have the following. So now we can determine the rate at which the radius is increasing. So we are given the volume in centimeter cubed. Yeah, everything is in centimeters, so we can substitute. So we have 400 centimeter cubed per second equals to 4 over 3 pi. In fact, I was supposed to multiply 3 and 3 there. So 4 over 3 times 3, we have 4. And therefore, we can substitute R. R we're given initially is 10 centimeter. Therefore, dr over dt. So we can determine our answer. Our solution, not an answer. Oh, this is squared, no? R squared. Dr over dt is equals to. So I have 400 divided by 4 pi 100. So 0.41 over pi. So 0.118. So it's centimeter. So it's centimeter per second, isn't it? So centimeter per second. The measure of the radius we measure in centimeter, but at the rate is increasing. It is at 0.315 per second, centimeter per second. It means we'll keep on increasing the radius at that rate. Right, I hope it makes sense.